Let's do another arc length problem. This time here we have this teardrop curve. It's an interesting parametric curve given by these equations. We want to find the length of just the teardrop portion of the curve, right, from here to here. Of course, that means we have to find the two values of t that lead to this self-intersection. Now, it helps that we have the graph, right? Helps that we have the graph. If we didn't have the graph, we'd have to do some work. One of the things we might want to do is actually think about plotting it, right? We might want to think about finding things like horizontal and vertical tangents, for example. So we could calculate dy dx and find those two vertical tangents. Find the horizontal tangent down here. How do we find the point of self-intersection, right? I mean, in general, for any curve, if you're looking for self-intersection, right, you're looking for, you know, any kind of point where you have the same x and y values for two different values of t. And so typically you need some sort of, you know, symmetry. Either what's going to happen is you know, they're both simultaneously 0, or you're going to have that, you know, both of these functions have to pass through the same point more than once. It's a little bit tricky to nail down these self-intersections in general. But here we can see that x is equal to 0 3 times at 0, 1, and minus 1, right? Here, plus or minus 1 will give me a 0. Y is equal to 0 when t is equal to plus or minus 1. Now, you can see that that intercept here corresponding to t equals 0. If I put t equals 0 in here, I get minus 1. That 0 minus 1 is this point down here, right? That's t equal to 0, down there, right? And so we can try a few other points. We could try like t is equal to, well, we know t equals 1. Let's see, if we put t equals 1, we get 0. If we put t equals 1, we get 0. Same thing for minus 1. Maybe we want to get some idea of like the direction of the curve. Not that it matters, but let's say we put t equals 2. This will be positive, right? So will that? If t is minus 2, this actually comes out negative. So for t equal to minus 2, we're somewhere over here. Plus 2, we're over here. So minus 2, minus 1, 0, 1, 2. So at least, you know, if we need to know it, we have some idea of the direction of travel around that curve. We go around like that. And we know that that point in the middle, right, that 0, 0, corresponds to both t equals minus 1 and it corresponds to t equals plus 1. Okay? So if we're trying to get the length of the teardrop, well, we should go from minus 1 to 1, right? So that suggests that the length of the curve should be the integral from minus 1 to 1 of the square root of x prime of t squared plus y prime of t squared dt. Okay? Now, because we have the picture and we can see the symmetry, I mean, you can kind of see the symmetry from the equations. You could also argue that the length, I could just go from 0 to 1 and double, right? Which suggests that probably we should get an even function under the integrand. But, well, let's confirm. Okay? So we have to go and actually calculate these things. So x prime of t. Now, don't do product rule. That's t cubed minus t. So we get 3t squared minus 1. Y prime of t is 2t. Okay. So what I get is the integral from minus 1 to 1. So x prime squared, I got to square that thing. I get 9t to the 4. Cross term is going to be 6, right? 3t squared plus another 3t. I get minus 6t squared plus 1. And then I got to add in the y squared. I got to add in the 4t squared. Okay? dt. It's not looking so good. I mean, we can see it's even. That's going to help us out, probably. We can simplify at least. So we get 9t to the 4 minus, so now it's going to be minus 6 plus 4 minus 2t squared plus 1 dt. And okay, so this is one of these times where we hope maybe things have been set up for us so we can factor. Can we factor? Let me see. Well, is it easy? Yeah, it's hard to tell. We can come over here. If you're stuck, right, there are tricks. It's hard to, when you don't have a 1, I mean, also it's degree 4, but only even powers. So it's like a quadratic in disguise, right? We can solve for t squared. So let's think about this. Quadratic equation tells me that that's going to be equal to 0 when t squared is equal to 2 plus or minus, let me see, so it'll be 2 squared, 4. Oh, that doesn't factor, right? Because I'm going to get minus 4ac, 4 minus 36 suggests that that doesn't factor. Which leaves me with an integral that I can't necessarily evaluate. At least I can set it up. But if I wanted to evaluate, I probably have to use numerical methods. I'm going to have to ask the computer. Either that, or I've made a mistake in my algebra somewhere. But I don't think I have. I think we just have something here where the only way we can actually evaluate this thing is numerically.